Hi there and welcome back to Triplicate, and today, as you've probably guessed by now, we're back on the remote control lorry, the big rig. Now last time we got it so we could use the standard remote control to drive the back wheels and the steering through the Arduino. So now we want to be able to get the back wheels and the steering to work as we want. I thought we'd have a look at the back wheels first. Now you'll see the tractor unit, or the base of it, is screwed down to a board to hold it in place while we're doing these measurements, because we want to measure the wheel speed. And zoom in on this, you can see here there's a little piece of error board with an LED there, and behind it, you'll have to take my word for it, a photodiode like that. And very fortunately, as you can see, the wheels have holes in them. So the LED shines through the holes, and as the wheel turns, the light from the LED is let through and blocked off, giving a nice AC signal that we can measure the speed from, the speed of rotation of the wheel. Okay, the first thing we want to know, I think, is the kind of voltages and currents we're going to be talking about to get our truck to run at realistic scale model speeds. So here we have a spreadsheet which gives some calculations. Now I've taken 1 mile an hour as the truck road speed and 100 miles an hour. So 1 mile an hour, we probably lower than we actually need for manoeuvring, specifically reversing, and apparently, given the top spec engine, these things will get up to 100 miles an hour, which is a terrifying thought. They were scary enough at 75. So we want to do our calculations in meters and millimeters per second, because that's easier to calculate in than miles an hour. So here we convert truck road speed in miles an hour into meters per second. And to do that, you divide the miles an hour by 2.25, so we get 0.44 and 44.44. Okay, so here I got some pictures with dimensions on, and they give the exterior width as 102 inches. And putting a tape measure on the trailer of the model is 3 inches wide, which gives us a scale of 34:1. So we are probably more interested in the model speed in millimeters per second, because I anticipate the slow speed giving us more trouble than the high speed. So now we look at the model speed in millimeters per second. So the slowest is 13 millimeters per second, and 100 miles an hour equivalent is 1.3 meters per second, which is actually travelling some. So then I measured the wheel diameter as being 35 millimeters, which gives us near as, damn it, 110 millimeters circumference. So the wheel revs per second then become, at the slowest speed, about a tenth and a ninth, and at the fastest speed about 12 revs per second. And looking at our sensor, now there are 10 of those holes in the wheel, so the frequency we measure at the sensor will be 10 times the revs. So at the lowest speed we have 1 and a bit hertz, which might not be too easy to measure, but at the fastest speed we've got 118, 119 Hertz. So now we know how fast we want our wheels to go round. Okay, so I've refined the code for the PWM drive to give us a little more variation in what we can set the drive to. So okay, and I've changed the display, so now we have VO, which is the power supply. This is the supply voltage to the motor and the driver chip and everything. Drive is the drive out of PWM amount out of 255, and VRS is the voltage across the sense resistor. So I have the oscilloscope on the photodiode, so we should be able to pick up measure any speed, and I am now going to start turning up the wick, as they say, the drive. So 2, and we can start to hear it singing, but it's not going round. Now we're starting to register some current, but not much. Okay, we're increasing the drive and increasing the drive, and still it's not started going round. The bursts of noise you see on the scope are the scope picking up the RF, the radio control. Oh, come on. Ah, and there we go. It starts, but it's actually started, if we measure the frequency, if we look at the frequency, and it's doing about 130 Hertz, which is actually faster than the top speed, so it won't only start at top speed. So we've got a problem there. Let's just start slowing it down. So at 22 it's actually died. I can't. It starts if I poke it and start it, but it's so the slowest is about 30 Hertz. So that isn't going to cut it. That's not what we want. Just out of interest, if we were to measure the current, would we detect that it's stalled? Only 34 to 38, that's not a lot. So we might struggle to detect the current as well. Okay, so we seem to have real problems getting this motor to run slowly. And thinking about it, I thought, well, in the automatic cat feeder project, we managed to get the motor to go around once in 2 days, and that's pretty slow. So that one was driven by pulses. So what happens if we try driving this motorbike with pulses? So what I've done is abandon the Arduino's built-in PWM function and just fired 3 millisecond pulses. Okay, there we go. So it's moving the wheels, but it's not moving them round, they're just bouncing off whatever and back again. That's the problem. We've got to provide enough pulse to kick the wheel on a small amount. So should we look at the code here? What have I done? I believe what I've done is, so I won't go into the code, but yes, that's a 2 millisecond pulse. So if I change it to a 3 millisecond pulse and we try again, there we go, and that's going round, and you can see I've stuck a piece of tape to the wheel, and you see that's going round pretty slowly. Yeah, around 5 seconds of rotation. So that's probably about the speed we want. Now if we look at the scope, the top pulse is the drive pulse, that's when it's on, and the bottom pulse is the current sense. So if we actually zoom in on that, what we can see, and I know the current level isn't always the same, it depends where the brushes are on the commutator, but it takes some time for the current to build up, and that's 2 milliseconds a division, so that will be about a millisecond for the current to build up. So that's our problem with PWM. What effectively happens is the armature of the motor behaves like a big inductor, and you apply power to it, and it takes some while for the current to come up, for the impedance of the inductor to drop down. This is not a problem at DC, but when we're using PWM or pulses, a lot of our voltage is just being, not absorbed, but taken up with this inductance. So can we somehow adapt this to produce variable speed? That's the next step. So let's see if we can actually control the speed of our wheels from very slow to as fast as we want it. So the way we do this is we maintain 2 counters, a speed counter and a pulse counter. Now here we're working in percent up to 100, and the speed counter is 37%. So the speed counter we add 37 every time, and the pulse counter we add 100 to when the speed counter is greater than the pulse counter. So you can see on the graph, the speed counter is the blue, the pulse counter is the light orange, and we output a pulse when we add our 100 to the pulse counter. And so when the speed counter is higher, obviously the pulse counter will have to increment more often, and we'll get more pulses, and that way we can control our speed. Okay, so I've implemented that scheme of generating PWM, and I've made it so the speed will just increase gradually from 0 to a maximum value, then go back and increase again, just to see that we can actually get a full speed range. So shall we send that to the Arduino and put the scope back? So here the bottom trace is the photodiode, Oh, there we go. No, it does that. So, starting again. And it's increasing, and that sort of speed. The optical speed sensor isn't working terribly well. Okay, the top pack traces the drive pulses. So as we get faster and faster, at about 50 Hertz. And so what I've done at about third speed, it switches from 3 millisecond pulses to 2 millisecond pulses, and at about 2/3 speed it switches from 2 millisecond pulses to 1 millisecond pulses, just to try and smooth it out a bit. Okay, so that's maximum frequency, so we're going somewhat faster than we need. And faster and faster and faster. And it's gone back to minimum speed, and off it goes again. So I think that's okay as far as it goes. Now I'm on the point of abandoning trying to measure the speed from the current draw. It just doesn't seem to be doable when we're actually using PWM like this. And I have another optical sensor on order, a reflective one, so when that comes I'm going to try and see if we can rig that to measure speed. So I think at this point I'm going to leave the back wheels and the drive and move on and have a look at the steering. Okay, so yet another day goes by, and this video is turning into a bit of a marathon to make, if not to watch. However, yesterday the postman brought a little reflective opto sensor, and I'm going to have a play with that off camera and see if I can turn that into a wheel speed sensor. So I thought at this point we'd get on and have a look at the steering. So what I've done is I've just connected my power supply across the steering motor, these two clips, via the multimeter on amps to my bench power supply, which is over there, which I am just using the current limit to control the amount of current going through the motor, and that current you will be able to see on the meter. So here we go. I'm looking at this. I think you can see the wheels alright. Hard to tell. So I'm now going to increase the current from 0 oh no, yeah, there we go. Oh, it did something. moved a bit, but only a bit. And that has gone clonk straight to, that's as far as it goes, full lock, which was at about 700 millivolts. And if I gradually drop the current down again at about 100 millivolts, the wheels flip straight to back to straight on. And just for completeness, we will put these crocodile clips on here and do it the other way around. So we start with the wheels straight and increase the current. Oh, slight movement to 600 milliamps. Until clonk we get to nearly 900, and that's full lock. It's not going any further. And if we reduce the current, clunk straight back at sort of 50 or 100 milliamps. So that is not very conducive to being able to control the wheels gradually. Now I can fiddle around with applying pulses to them and see if that does any good. Failing that, down that hole, I don't know whether we can see that, hopefully you can see that, is the spindle on which the steering turns, and there's a sort of cross-shaped bit of plastic in there, so I could possibly get a pot with some kind of a thin shaft down there onto a pot, but then again there's only what, maybe 45 degrees steering end to end. And the other option is this guy, which is a servo, which I actually bought ahead of another project, and I don't know how powerful it is. I've not actually even plugged it in, but assuming it's got enough power to pull the wheels round, just away with this whole motor assembly and put that in there. So we have three options, and I shall ponder them along with trying to mount a speed sensor, and I will give you my conclusions in the next video. So I guess it's been a bit of a frustrating one. We've made some progress. So on that note, I will leave you for this video. Please subscribe if you like the channel, maybe leave a comment or a thumbs up, and I'll see you next time. So for now it's goodbye from Triplicate, home of interesting electronics.